work. Okay. Okay, great. Yeah, so what I'd like to talk about is testing quantum computers and quantum mechanics, but there could be a different title to this talk, which has to do with the extended quantum church-turing thesis, which is a thread that goes through all of quantum computation, through the history of quantum computation. So let me just say a few words about it. Well, everybody here knows the extended church-turing thesis. It says any reasonable model of computation can be simulated on a probabilistic Turing machine efficiently. And the view that we as computer scientists inherited was really the logicians' view. After all, Church and Turing were logicians, where we thought of a Turing machine as describing the set of humanly computable functions, infinite amount of paper, infinite tape, lots of pencils, read, write, head, etc. Okay, but there's another view of this thesis, which is more physical, and this goes back. One could argue that the roots of this go back a very long way to the days of Newton. Where with this notion of the clockwork universe, of this mechanical universe, and the way this view, and moreover, this view, of course, pervaded, all of science and even mathematics, and so you could sort of say, well, maybe the logician's view was also in some way influenced by this, and the way we would understand the extended church-turing thesis through this physical view is by saying, well, this clockwork universe could be formally described by saying, look, once you make your theory robust to noise, essentially you're saying nature is described by, okay, so you would say, well, nature is described by local differential equations, but then once you make it robust, you'd say it's described by a cellular automaton. And of course, a cellular automaton is equivalent to a Turing machine, polynomial time equivalent. And so this extended church-turing thesis sort of is a consequence of this view of physical reality. Now, okay, so the ironical thing is that even though the theory of computation came about, started second half of, the 20th century, already physics had moved on to a different theory, which sort of is directly at odds with this view of the universe. And so what quantum mechanics posits is that, if you have n particles or n qubits, sort of the state of the system is described, is described by a exponentially long vector in this exponential dimensional Hilbert space, right? So, and it's a complex vector space. And moreover, if you were to act locally on a pair of particles, a pair of qubits, then basically what you're doing is you're applying some unitary transformation to this entire Hilbert space, thereby updating all the exponentially many complex amplitudes which describe the state. And so the action, rather than being local in this form of a cellular automaton, is instead, so where you are acting on is these particles, but behind the scenes, you're really acting on this exponentially large space. And so it seems as far from this cellular automaton or clockwork universe as one might imagine. But then there's a catch to all this, which is that we have very limited access to this, to this Hilbert space. So when you perform a measurement, you only see a classical string X with probability alpha X magnitude squared. So if it's n qubits, you would see only an n-bit string. So this, this really interesting dichotomy was pointed out by Feynman in this beautiful paper. It was actually a talk at a workshop which got transcribed. So the talk was called Simulating Physics on a Computer, where by computer he meant classical computer. And what he pointed out is apparently you need exponential resources to simulate an n particle quantum system. And then he asked, is this inherent, or is it possible that there's a different description of quantum mechanics which would give you an efficient simulation? So, is it that the physicist got a extremely cumbersome description of something that was much simpler? And then he said, well, and if not, could a computer based on quantum principles perform such simulations? So, so the early years of quantum computing, were devoted to showing that quantum computers violate this extended gesturing thesis in a robust way, and eventually led to this formulation of what I call the quantum extended gesturing thesis, so a revision of the extended gesturing thesis. It also provided a new regime in which to test quantum mechanics. And now in the more recent times, what people have been pursuing is an experimental violation of the extended gesturing thesis, which they call quantum supremacy or quantum advantage. And very, very recently, there's also the beginnings of this question of whether even the quantum extended gesturing thesis holds, or whether is it the case that once you extend beyond this to quantum gravity, would this challenge the quantum extended gesturing thesis? So I'll sort of take you through this, this thread that goes through the field, and hopefully also illustrate some of the interesting work that's been going on recently. Okay, so I've tried to organize this talk so that it's possible to follow it without getting too deeply into quantum notation. So but please bear with me. Okay, so how did this what does it mean that quantum computers violate this extended gesturing thesis? So there are three aspects of this thesis that you really have to worry about. One is you have to show that quantum computers, that they are programmable and they are efficiently programmable, that they are digital, so they are robust, okay, that they're robust to errors, and that they are not efficiently simulatable classically. And so, with my student Ethan Bernstein, we did sort of the early work on this by showing, one, that there's an efficient universal Turing machine, quantum Turing machine, that it's robust to inverse polynomial errors, and that it gives you super polynomial speedups on some challenge problem. So in an Oracle setting, and we realized early on that we couldn't really get a complexity separation because quantum polynomial time is neatly trapped between polynomial time and polynomial space. By using what physicists would call the Feynman path integral, what we would just say is exploring all possible paths in a non-deterministic or probabilistic computation. Okay, and then over the next few years, this violation of the extended gesturing thesis was really made much more robust. So in terms of speed up, the speed up was shown in the most dramatic way possible, given this fact that BQP is neatly trapped between P and P space, by Peter Shaw, where he showed that two of our most challenging computational problems, for which we are fairly confident that they are hard classically, that they have polynomial time quantum algorithms, namely factoring discrete log. In terms of robustness, there was this theory of fault-tolerant quantum computation that was developed, which showed that as long as the noise is random, that it affects random qubits, that you can actually make your quantum computation robust to constant rate of error, which is sort of the best you can hope for. And then in terms of programmability, there was a sequence of results, initially showing that, so you had to show robustness by saying different models were equivalent, like quantum Turing machines and quantum circuits. But then there are also other models that you can come up with where you say, well, look, the natural way you would want to think about a quantum system is by describing the local Hamiltonian. This particular description also gave you an equivalent, efficient. You could efficiently simulate local Hamiltonians and vice versa. And eventually, the model that was developed of a quantum computer is actually a very beautiful one from the point of view of experimental implementation, which is that a quantum computer is basically a set of qubits which you stabilize in some way. And then you have an external classical computer which issues commands saying, perform the following gate between these two qubits or those two qubits and so on. And you can have these instructions in parallel. And so you provide an input to set up the state of these qubits. You perform these gates by actively issuing commands, and then you measure to see the output. And your output, of course, is going to be a probability distribution. So you're going to get a sample from a probability distribution. So this was quite a sequence of steps towards making this model robust and saying, look, this is a robust violation of the extended Church-Turing thesis. Now, after that, things went a little bit further, beyond local Hamiltonians. There was a question, well, what about other formulations, such as topological field theory and quantum field theory, and can you actually, does this give you a way of going beyond quantum computers? Maybe can those be simulated? And actually, basically the answer is yes, they can be simulated. And so eventually, these demonstrations seemed sufficiently convincing that one could come out and say, look, we can replace the extended Church-Turing thesis by the quantum extended Church-Turing thesis, which says now, any reasonable model of computation can be simulated on a quantum Turing machine, efficient. Okay, so now let me say a little bit about what this has to say about testing quantum mechanics. What this violation of the extended Church-Turing thesis, what it says about the foundations of quantum mechanics. And so this is something that we were hyper aware of even in the early days of quantum computing. And this was maybe, for many of us, more than half the motivation, of thinking about these topics. And so, and just to put it in context, there is, let's look at the situation from the point of view of us, quantum, who we can think of as classical verifiers. So we are bounded by polynomial time, etc. We can only see classical information. And then there's this quantum world inhabited by these n qubits, which are extremely powerful. There's an exponential Hilbert space. And we get to sort of interact with it. But then there's this fundamental theorem of Hulevo's, which says that basically, if there are n qubits, all you can get out about this exponentially complex state of the n qubits is n bits of information. that's all we'll ever get to see. That's all the information we can ever extract about this quantum state. And so, even in those early days, we realized that there was something new that quantum computation would give us about this situation. And I was actually a little surprised recently when I went back and looked at our papers, and we actually put this down in even though this was our motivation, we actually said it explicitly. So we said something like, look, naively, you might think that it's impossible to experimentally verify this exponential size of the Hilbert space, because it seems like nature is covering her tracks and giving us only linear amount of information about what's going on behind the scenes. However, if we have an experiment demonstrating an exponential speed up by quantum computation, then implicitly we'd have verified that something like an exponentially large Hilbert space must exist, because if we are doing the computation very quickly, then the width of the computation must be exponentially large. Okay, so later, as time went along, the way we formulated it was as follows. We said, look, we should think of this exponential growth as perhaps the most counterintuitive aspect of quantum mechanics. And so, since one of the goals of physics is testing its limits in limits where our intuition doesn't work well, like in the limits of high energy or very small sizes or very large velocities. And when physics is tested in these limits, something new often is discovered. So now we have a new limit in which to test physics, which is the limit of high complexity. And so this is the way one should see these recent experiments on quantum supremacy. They are really an experimental violation of this extended string thesis. And even though they are thought of as also as a milestone on the way to practical quantum computation, it's maybe even more interesting as an experiment in fundamental physics, as trying to explore and verify this, that quantum mechanics holds in this limit of high complexity. Okay, so what is this? So in the next few slides, I'll describe a little bit about this experiment and where we stand today with respect to it, and then I'll tell you more about the theory of of interactive quantum protocols and how how we can go farther in this direction. Okay, so Google's it was roughly 52 qubits. So they have this Sycamore processor, with qubits as these crosses, and these rectangles are the adjustable couplers between them. So this experiment probes this 2 to the 52 dimensional Hilbert space, and basically, why 52? Well, it's a number that's large enough so that 2 to the n is impressive, small enough that you can simulate on a classical computer, supercomputer. And so what does this experiment consist of? Okay, so here's a large scale overview of the experiment, and then I'll say a little bit more about it. So basically, what you do is you set up your input, you run the quantum circuit, you sample, and now you sample, meaning you get a random output, and you want to ask, does the output of this typical quantum circuit, does it betray a detectable quantum accent? So can you tell whether it came from a quantum circuit or a classical circuit? And we want to say, no, this must have been quantum. It couldn't possibly have been classical. Okay, there are a few issues with this. One, it takes exponential time to detect this accent. Hence, you need a classical supercomputer to run this. To actually analyze the experiment. We don't know for certain that classical computers cannot fake such a quantum accent. But there's evidence that they cannot, and so I'll describe to you how you detect or try to detect whether it's really a quantum accent, and then how you might fake, what the evidence is that you can't, and what's the gap in this evidence, Okay, so what do you do in this experiment? You fix once and for all a random circuit, a random quantum circuit, say of depth about 20, it's 52 qubits. You initialize each of the qubits to the 0 state. You run the circuit, you measure the output 52 qubits to get a 52-bit string, classical string, X. And now, since you've fixed your quantum circuit C, you use a supercomputer to compute the probability with which C would have output X. Okay. And now since you repeat this experiment many times with the same C, you collect a sequence of samples X1, X2, etc., and you check whether the sampled X's are consistent with these probabilities. Meaning, you somehow come up with a score which says, is this likely to be? Are these X's likely to have been sampled from this circuit C? So how would you ever do this? So to check whether the sampled X's are consistent with the probability that this quantum circuit C would have output them, you use a score, a statistical measure, which is linear cross entropy. It's just a simple score. It's just the expected value of the probability that the circuit C would have output X. Okay, so what's the intuition? Higher probabilities X should show up more often than low probability X's. So for example, if the circuit C outputs uniformly random strings, then the expected value of this probability would be exactly 1/2 to the n, because every X has probability 1/2 to the n, right? For a random quantum circuit, you can show that this expected value should be 2/2 to the n. Okay, so if you take the expectation over all circuits, then this value should be 2/2 to the n. Okay, and it's sharply enough concentrated so that you expect pretty close to 2/2 to the n. So what did Google do with its experiment? It collected lots of samples, millions of samples, and then what they got for this measure was 1.002/2 to the n, roughly. Okay. Now you would imagine that at this point you would say, well, this was a failure. Let's try again. But what Google was saying was, look, we have a lot of noise in our experiment. The quantum circuits, they are still not very, even though you get 99.5, let's say, fidelity for every gate, but 50 times 20 is about 1,000 gates. So by the time you get to that large a size, you're going to get plenty of errors. So they wanted to say, well, this is sufficiently far from 1/2 to the n that it really does show that this should be convincing. Okay, so why should we believe this? On the face of it, this seems not that convincing. So there are a couple of theoretical justifications. The first one is of a complexity theoretic nature. It's sort of a worst case to average case reduction. It says. And it basically says, if you can sample from a distribution pretty close to the output distribution of a random quantum circuit, then the polynomial hierarchy collapses. The problem with this kind of result, which has been improved over time, is that even with the latest improvements, you have to be extremely close to the output distribution, nowhere close to this 2 versus 1.002. So there was another hypothesis, which was another way of justifying it, due to Aronson-Chen and Aronson-Gunn, which is to directly go for this intuition that quantum circuits often generate heavy outputs, high probability outputs. And so they came up with this hypothesis which said there's no efficient classical algorithm that can guess with probability half plus something exponentially small whether the probability of outputting X under this circuit C is higher than median probability or lower than median probability. Okay, and under this kind of assumption, roughly this assumption, they were able to show that actually you don't have a classical algorithm that can that can pass this this statistical test, the linear cross entropy test. And the intuition behind this was that they were sort of suggesting the best thing you could do is Feynman path integrals. Just try all possible computational paths. That's the best you can do. If you don't do all that, you can't get such a this kind of you cannot tell with any significant probability over half whether it's higher or lower than median. So since then, a few things have happened. There was a sequence of classical spoofing strategies, and this was a particularly convincing one. It sort of said for the particular sizes that of experiments that Google ran, you could actually classically spoof them in a few seconds on a supercomputer. So your 52 qubits versus a supercomputer, and okay. So you could say, well, is that it does that is spoofing it, so but on the other hand, you could also say, well, look, if instead of 52 qubits you went up to 60, 70, 80 qubits, this would no longer work. There was a more recent paper by Gao et al. From Harvard, MIT, which sort of said, look, there's a very nice reason why you can refute the Aronson-Gunn hypothesis the way it was stated, exponential in the number of qubits or the number of gates, where they showed that you can actually get a bias which is exponential in the depth of the circuit instead. Now you could, there are several ways of dealing with this. You could sort of go back and say, well, maybe we should modify the hypothesis to be exponential in depth, but at this point, you have to sort of start asking, is this, to what extent does this really show, after all, quantum supremacy, it's an important scientific experiment. It must be refined to eliminate loopholes. And we should really say, look, it's a little bit like the Bell inequalities, where it was an experiment done over several decades and refined until you could get rid of all loopholes. And so this is an experiment that's going to be repeated over and over again with better and better hardware, but also better and better complexity theory underlying it. So we have to find ways of doing this where we can say it really does show that quantum mechanics holds in this limit of high complexity. So in particular, one thing we have to do is now be able to scale up our protocols. So the classical verifier had better be more efficient so that we can work with 100, 200, 1,000 qubits, etc. Okay, so now, at this point, I'll turn to the next part of my talk, which sort of reviews what's been done with respect to classical protocols by which a classical verifier sort of interrogates a quantum computer and an untrusted quantum computer to perform several tasks. Okay, so basically, one way you can think of this sequence of results is they provide a sort of a cryptographic leash for quantum computers. Okay, so you have your classical verifier here, and who's trying to interact with a quantum computer, but untrusted quantum computer. So the quantum computer is more like a black box. It's very powerful, potentially. It's also not very communicative because, it has this exponential amount of information sitting inside of it, but it only shares n, linear number of classical bits. So the main idea behind this entire line of work is that there is such a thing as post-quantum cryptography. There are classical crypto systems that even quantum computers cannot break. And so, moreover, moreover, these classical crypto systems have a secret key, so that if you have the secret key, then you can decrypt messages classically efficiently. But if you don't have the secret key, then even a quantum computer cannot decrypt these messages, right? So in a certain sense, you can use crypto to give this classical verifier an advantage over the quantum computer. And so using this kind of primitive, there are a number of results. There's a proof of quantumness, a way to verify that this computer really is quantum and that nothing classical could have duplicated these results, unless it was exponentially powerful. Certifiable randomness, verification of an arbitrary quantum computation. How would you know that the answer that your quantum computer is giving you is correct? Fully homomorphic quantum computation. So how do you delegate your computation to the cloud while maintaining the privacy of your data? Device-independent quantum key distribution from computational assumptions. So even quantum cryptography, if you want to carry it out, but using computational assumptions. So now there's one thing that you have to, one has to realize in as one tries to carry this out, which is that there's a right way and a wrong way to deploy this post-quantum crypto. So the wrong way would be to cripple the quantum computer by forcing it to play on the classical verifier's turf, because that doesn't help anybody, right? So then why play with the quantum computer at all? So the right way is we want to make sure that the verifier is an advantage, but we still allow the quantum computer to play on turf where it can exercise its unique quantum capabilities. So it can be in superposition, there can be quantum interference, etc. So you have to work at, you have to think in a different way in order to create this sort of cryptographic leash for quantum computers. And so at the basis of all of this work is something called the Qubit certification protocol. So this is a protocol in which your verifier interacts with the quantum computer, a few rounds, and at the end of this, the quantum computer ends up with a qubit in this kind of a state. So what is this state? It's either an equal superposition of 0 and 1, or it's a superposition of 0 and 1, which is still where there's a phase of -1 here, right? So this classical bit B is either 0 or 1, and depending upon what it is, you either have a phase or not a phase. So the quantum computer has this qubit, which is either in the plus state or in the minus state, with equal probability. The problem for the quantum computer is it does not know this bit B, so it doesn't know whether it's in the plus state or the minus state. All it knows is an encryption of B in this post-quantum crypto system. Now, what the quantum computer can do is then send this encryption across to the verifier, who can use the knowledge of the secret key to figure out what this bit B is. So now you have this interesting asymmetry between these two players. On the one hand, the quantum computer is able to deal with quantum data. It's able to deal with quantum states and manipulate them and create this quantum state. On the other hand, it has no idea what it is. And the verifier has no ability to manipulate quantum states, but knows exactly what the state is. So from the viewpoint of the quantum computer, being in the plus state or the minus state with equal probability is, the density matrix corresponding to that is the identity. So it's a maximally mixed qubit, which means it's like a totally random qubit. Okay, so there's no information at all about this qubit that the quantum computer has. So let me just say a few words about how this comes about. I'll give you a sketch of what how this comes about, and then based on that I can say a little bit about how one applies this. So the basic object that we use here is called a trapdoor claw-free function. So a trapdoor claw-free function is just a 2-to-1 function. So I should say I'm simplifying things a little bit, but this is really the main idea here. So this function f is a 2-to-1 function, meaning, so for example, if x0 maps to y, there's also an x1 that maps to y. It's easy to compute. So given x, it's easy to find f of x. It's hard to find a claw. It's hard to find any x0, x1, and y so that both of these map to y. But of course, with the knowledge of the trapdoor, you can invert. So you can, given y, you can compute both x0 and x1. So you can implement these based on learning with errors, which is one of the well-known post-quantum crypto systems. So learning with errors is just noisy linear equations. So you're given you have n unknowns modulo some q, and you're given many more than n linear equations, except each of them is noisy with a small amount of Gaussian noise. Okay, so now here's an outline of the protocol. So the verifier first specifies this trapdoor claw-free function. In the case of LWE, it just provides an LWE sample, which is a single vector. Now the quantum computer sort of somehow does something. It samples a y, okay, and sends that back to the verifier. The verifier sends a challenge 0 or 1, 0 saying, give me back a pre-image, x0 or x1. And then if the quantum computer gives back this pre-image, then of course the verifier can check by just computing f of x and checking it that it's y. Or if the challenge is 1, then the verifier is asking for an equation connecting x0 and x1. So some d such that d times x0 plus x1 is 0. Some equation, which again the verifier can check by now using the secret key to figure out what x0 and x1 are given y, and then checking that they satisfy the equation. So the quantum computer can answer either challenge. Because of the post-quantum crypto properties, we can say that no polynomial time quantum or classical computer can answer both challenges, that is, provide both x and d. So now, based on this second fact, we can say no classical computer could possibly succeed in this protocol with probability much greater than half. So it's a funny thing we are saying. We are saying, look, this impossibility statement is symmetrical in classical and quantum, but somehow it allows quantum computers to succeed in the protocol, but it does not allow classical computers to do so. And that has to do with the fact that a classical prover can always be rewound. So in other words, if there was a classical protocol, we'd run through with asking for a pre-image. And then what we would do is rewind the computation, meaning we'd rewind the internal state of this classical computer to what it was just after it sent y. And now we'll issue the other challenge and ask for an equation. And now, and we'd get back both an equation and a pre-image. And this would allow us to break the quantum crypto system. Okay, so somehow we are using the fact that classical computation, they have a history, they have a trace. You can trace how the program worked, whereas in quantum computation, you have no way of tracing what happened. Okay, so how does this work? Well, it's sort of easy. This is if you know of Simon's algorithm, it's using some of the same thought process that went in there. So the quantum computer sets up a superposition over all x, then it computes y. So it has two registers, one containing a superposition of all x, the other containing y. Then it measures the second register, so it samples a random y. and it's left with a superposition over pre-images. At this point, you can measure this pre-image register in the standard basis to get X0 or X1 with probability half each. So that's not a surprising thing. You could have done this classically as well. The interesting thing is if you measure in the Hadamard basis, then you obtain an n-bit string D such that D inner product with X0 plus X1 is 0. So here plus is bitwise addition mod 2. And so this is a genuine equation, connecting X0 and X1. And so now for a proof of quantumness, we have to show that, that it's hard to obtain both a pre-image and this equation, right? So we said trapdoor claw-free function, meaning it's hard to obtain both pre-images. So to show that even obtaining one pre-image and this equation is hard, we have to show that there's a new kind of, it's a kind of a hardcore bit property, but it's a new kind of hardcore bit property, which is called an adaptive hardcore bit. So basically what we're saying is, look, the quantum computer gets to see the LWE sample. It gets to see what our classical description of this specification of this trapdoor claw-free function is. And only after that does it choose, come up with a pre-image and an equation. So we want to say, that knowledge of the pre-image and a better than 50-50 guess for this equation implies an efficient algorithm to find a claw and therefore break LWE. And the assumption here is that the adversary gets to choose D, meaning which bit is the hardcore bit, after seeing the particular trapdoor claw-free function, which is chosen by the verifier. Okay, so this proof actually relies heavily on these properties of LWE called leakage resilience, it's a beautiful property of LWE, which gives you a way of getting a handle on hardcore bits. So this is something that's been highly developed in the crypto community, and so that's what's used to show this property. Okay, so once you can reach into a classical verifier can reach into the Hilbert space of the quantum computer and say, look, even though you're completely untrusted, I know that you've created this qubit, which is either in the plus state or the minus state, right? 50-50. Then it turns out that you can use this to do certifiable quantum random number generation. So what is certifiable quantum random generation? So you start with a small number of truly random bits. You have your untrusted quantum computer. You perform certain tests on it. You run this interactive protocol, and at the end of that, you generate n bits, which are statistically random, right? So the interesting thing is that you certify that unless something went wrong, which can only happen with very low probability, so based on your classical tests, you certify that this particular string must be statistically random. It must have been chosen uniformly at random or close to uniformly at random, not pseudo-random, but statistically so. And in order to do this, you're actually certifying that this not only is this statistically random, but it must have been chosen fresh. It must have been freshly generated randomness, and it's random even relative to an adversary who is entangled with the quantum state of this quantum computer. Meaning, even an adversary who shares entanglement cannot. This string must look random to them. There are other things you can do with this cryptographic leash. So there are these two very striking results by Urmila Mahadev. One of them is showing how to do quantum fully homomorphic encryption. So again, where you can delegate a quantum computation to the cloud while maintaining the privacy of your data. And the other is the verification of a quantum computation. How do you verify that the output of your quantum computer is correct? Even though it's solving something exponentially hard and possibly not in NP. There's a very nice way of seeing that this verification can be done by using, there's a protocol of Fitzsimmons and Kashefi, which says, well, look, as long as you can create qubits, which are not just in the plus or the minus state, but it's in one of these 8 states where omega is an 8th root of unity, right? So your phases now, instead of being plus or minus, are one of 8 values mod 8. Then you can sort of plug into this protocol and just say you can verify an arbitrary quantum computation. And so Giorgio and Vidic sort of showed that you can replace the qubit certification protocol by you can add a couple of steps to it, and instead of creating randomly a plus or minus state, you can randomly create one of these 8 states and use that to verify a quantum computation. Now, there are a few other protocols I should mention. One is in the proof of quantumness, we needed an adaptive hardcore bit. It turns out you can actually get rid of this adaptive hardcore bit by modifying this basic qubit certification protocol to incorporate a bell test, this so-called CHSH game. So the bell test is usually a test for entanglement between 2 spatially separated players who share entanglement. But now what you can do is replace the space-like separation between 2 players with this computational hardness of the crypto problem. So essentially the same player holds 2 pieces of information, but they are, because of cryptography, it's as though the 2 pieces cannot communicate with each other. So the advantage of this is that you can now use other kinds of trapdoor claw-free functions, such as the x-squared modern, so something that's based on factoring instead of, so you don't need, of course, you don't need, when you're doing tests of quantumness, you don't need post-quantum crypto, but you can also you don't even need adaptive hardcore bits. So there's a recent implementation of both of these protocols with and without the adaptive hardcore bit on an ion trap quantum computation computer. So they had to, do an experimental innovation where they had to implement, to implement the protocol, you had to have this communication back and forth. So you had to do mid computation measurements, so intermediate measurements during the computation. So I should emphasize this is a proof of concept. So it's not yet scaled up to, so to scale up to cryptographic sizes, you would have to go up to 1,000 or a couple of thousand qubits and large depths. And the hardware is not there yet to implement these large number of qubits with sufficient fidelity. So this is sort of just a proof of concept saying you could do this if but now if you had large enough and high fidelity enough qubits, then you could do this. There's another sort of wrinkle on this, which is, well, in the certifiable randomness, this basic protocol, the qubit certification protocol, it gave you 1 qubit at a time. So could you make this much more efficient and generate n bits of randomness by changing the qubit certification protocol? And the answer is yes. it actually provides a test that the quantum computer has n qubits of memory. And what this does is it uses this leakage resilience of LWE to choose a 2 to the k to 1 function instead of a 2 to 1 function. And it turns out that to make this work, you really have to change the proof quite a bit, but there is an open question here. So you do get the randomness, etc. But what you'd like to do is actually certify. So in the Qubit certification protocol, there was a certification that the quantum computer holds a qubit in the plus or minus state. Now here, it would be nice to be able to certify that the quantum computer holds n qubits, in some random state, and it's quite plausible that these techniques get you there, but it's not done yet. So it's an interesting open question. I think it's interesting also because it says to what extent you can reach into this into your quantum computer. Okay, so let me wrap up with a discussion. So the extended chair string thesis sort of forms this thread through this field of quantum computation from the very early days in the early 90s up to now. So the early years were showed how to violate, how the violation of this thesis could be put on more and more robust ground, eventually leading to this quantum extended chair string thesis, which of course gives us a new regime in which to test quantum mechanics, and the recent experiments are an experimental violation of the extended chair string thesis. To go beyond these sort of experiments, we have to, one way around is to use a cryptographic leash, and through this cryptographic leash you can actually perform not just proofs of quantumness, but you can go well beyond that to perform all kinds of other tasks. And then in a minute or so, let me just say something about this whole notion of quantum gravity and whether it challenges the quantum extended chair string thesis. I realize that this may be, well, one, it's not something that I know that, I understand that well, except at a high level, but still there's something to be said about it. So let me just take a minute or so to say something about it in one slide. So, one of the basic challenges in physics is reconciling general relativity and quantum mechanics. And so there's been this this major sort of project, starting with Maldaceno's work in '99, called the ADS-CFT correspondence, which sort of says gravity and quantum mechanics are sort of two sides of the same coin. There are two views of the same reality in some sense. And so what it does is it gives a duality theory between gravity in d dimensions, called the bulk, and a conformal field theory of quantum mechanics in d-1 dimension, called the boundary. And there's a dictionary map which maps states of one to the states of the other and operators to operators. Okay, so now about 6-7 years ago, Lenny Susskind gave something called the wormhole growth paradox, which said, the volume of a wormhole in this bulk, sort of said, well, it's not clear what it corresponds to on the boundary. And he sort of suggested, given this paradox, he suggested the volume of this wormhole corresponded in the boundary to the computational the quantum circuit complexity, the quantum complexity of the corresponding quantum state in the boundary. This of course sounds very funny to a complexity theorist. So with Adam Boland and Bill Pfefferman, what we showed is that, in fact, either given this state of affairs, either the quantum extended Church-Turing thesis is violated in quantum gravity in the bulk, or this dictionary map must be exponentially complex. And both of these are sort of surprising, and they seem to provide some some new insights into this ADS-CFT correspondence, into this nature of quantum gravity. And then recently, Susskind gave a simplification of this result, providing a possible route to demonstrating some limited form of quantum extended Church-Turing thesis violation. Okay, so now it's the most interesting thing about all this is that formalizing some of these notions seem like they might provide a real insight into this subject that of this that physicists have been studying for these last 25 years quite intensely. And even formalizing what the quantum extended Church-Turing thesis looks like in the bulk in quantum gravity is an interesting subject. Okay, so with that, I'll stop here, and thank you very much for your attention.
All right, thank you very much. We've got a couple of minutes for questions. So if people would like to post a question in the chat, I can read it, or they can unmute themselves and ask it out loud. I guess I have a couple of questions. Maybe I'll start one off. So you mentioned violations of this sort of quantum extended Church-Turing thesis. Do we have a sense of what a more general model of computation might look like?
Yeah, so sorry, yeah, that's a very good question. That's what I was getting at in this last slide. When I said even formulate, when I said even formulating the quantum extended, this quantum extended Church-Turing thesis in the bulk. That's what I was trying to get at, just understanding what the model of computation there is, saying, okay, here's the model of computation, and it satisfies the quantum extended Church-Turing thesis, or it does not. I think this is a really interesting question, and I think it would provide real insight.
How does this relate to, I know, for example, when you've got two space-separated say provers.
Yeah.
We have different kind of models for what kind of like connection is allowed between, correlation is allowed between them. There's sort of, quantum provers, there's non-communicating, non-signaling provers.
Yeah.
Does this sort of generalization live somewhere in that?
Yeah. So
hierarchy, or is it sort of just like kind of an orthogonal kind of question?
Right. Yeah. Yeah. Good question. So I think that in general relativity, the observer matters, right? So there are different realities based on the observer, and so one of the the problems is how do you stitch together these realities, and how do you make sure that each one of them, so if for quantum mechanics to be true, each of their realities must there must be a Hilbert space, there must be unitary evolution from their viewpoint. But now they are different, each observer has their own reality, and so you must be able to stitch together these Hilbert spaces in some way. And so that's the issue, that's the basic issue at hand. And sorry, I'm far from an expert in all this, so I'm just speaking as a layperson, without really understanding much of what I'm saying. But that's, and so whatever model of computation one comes up with, one has to deal with all this, and so when we proved our results saying, either the quantum extended Church-Turing thesis is false or the dictionary map is exponentially complex, we just used it to sort of take the state from the CFD and map it across, and then say, look, because of the quantum extended Church-Turing thesis, we can now simulate everything without saying what it means, so just at a high level. But if you dip down into the theory and say, okay, but what does this really mean? Well, we don't really have a good answer to that, and it just feels like answering that question should provide serious insights.
Oh, yeah, no, it does sound interesting. That's great. All right, I want to give other people, anyone else, a chance who would like to ask a question. Okay, so since there are no other questions and we're out of time, I think we should thank Umesh again for the great talk. And yeah, and we'll, I guess, resume with the next session at hour.
Well, thanks very much.
And thank you again to Umesh.
Thanks for inviting me.
Thank you, Umesh.